Okay, hello. This is lecture 19 in the course. And today I'm going to speak about a pretty interesting topic, which is the W hierarchy, which is this hierarchy of hardness of problems as far as fixed parameter tractability is involved. And the basic idea is that we would like to look on, in some sense, the circuit complexity associated with the problem at hand. And the thing to remember is that if you think about the classical problem 3 sat, the formulas are very simple, right? They're just, O of clauses. Every clause has three literals, and then we take the end of all those clauses, and that's it. That's the formula, right? It's an extremely simple formula, but you can write more and more complicated formulas, and in some sense, or more and more complicated circuits, and you would like to capture the complexity of the circuit, right? Now, the most natural way to think about complexity of a circuit is to talk about the depth of the circuit, right? Um, a natural thing to say is, oh, well, let's just look on circuits that have logarithmic depth. The point is that if you look on circuits with logarithmic depth and you ask the satisfiability question on them, then you get the class NP, right? Because it's not hard to see that many of the standard NP-complete problems, once you write them down and you do the reduction to a circuit, you get a pretty simple circuit of logarithmic depth. And in fact, it would follow from the examples I'm going to show shortly. So logarithmic depth is out, right? Because in some sense it captures all of NP, and that's not a very useful distinction as far as complexity. So instead, we would like to look on a constant depth circuits, right? Now the problem is that if you're going to have a constant degree circuits, then by necessity you must have high degree nodes in the circuit, right? So in some sense, we would like to capture how many high degree circuits there are. And in fact, what we're going to do is we're going to distinguish between nodes that have degree 2 or higher, right? Degrees that have incoming degree larger than 2 are going to be heavy nodes or large nodes. And we are not going to allow too many of them. More formally, we don't care about the number. What we care about is how many different, if you look on a path from an input to the output, how many heavy gates are there on this path, right? And if there is a single, heavy gate, then we will call it class 1. If there are at most of all paths, there is at most 2, we'll call it it will be W2 and so on, right? That's the basic idea. But before we go any further, let's maybe first see an example. So consider the problem of independent set, right? So you have a graph, and you would like to build a circuit that has that output whether or not the graph has an independent set, right? So what you do is you're going to have n inputs, where the n inputs are just, for every vertex in the graph, there's going to be an input boolean, which is whether or not we take it for the independent set. And then what we do for every edge, we're going to have an OR gate, right? And the OR gate, so it's a bit confusing, but the OR gate is going to be the following. We take the two corresponding vertices, we take their negation, this is the negation, right? And we take their OR, right? And the intuition is that the only bad case for this gate is if we pick both vertices, right? If we pick both vertices, then we negate them both, we get 0, 0. We take the OR, we get 0, right? So if an edge gets 0, it means that the set is not independent, right? So you take all the gates that corresponds to the edges and you put them into one big AND gate, right? And notice that this is the only heavy gate, right? So that's it, right? And this is clearly a circuit for independent set. It's a circuit of depth, I don't know, depth 2 or depth 3. We don't really care that much on the depth as long as it's a constant. It's a constant depth, and on any path there is only one large gate, right? So this circuit is going to belong to the class W1. Okay, and notice, by the way, that this is a circuit. This circuit is satisfied if and only if the graph has an independent set. Well, every graph has an independent set. You just take the empty set. So we need to force the number of ones in the input, right? So we're going to speak about the weighted version of the problem, and that's going to be our parameter. So think about an independent set and k, right? I'm asking you, is there independent set in the graph of size k, right? Which means that is there a satisfying assignment for the circuit where exactly k inputs are 1. Okay, so that's going to be kind of our classical problem. Okay? Okay, so that's the idea. And of course, the intuition is that, problems can get more complicated, right? You will need circuits that have bigger depth with more large gates. And that would give us the distinction. Okay, here is another example, right? So this example, the example on the right, what is it? So this is a dominating set. And let's see why it's a dominating set. Again, every vertex is an input. And now every vertex in the graph is an OR gate, which goes, and it gets an input from all itself and all its neighbors, right? And it just says it's an OR. It says you have to pick one of them, right? So this gate is 1 if and only if this vertex is being dominated by the selected set of vertices, and then you just need to take the end, right? And notice here that here we have two, on any path we have two heavy gates, right? Because the gates in the second row, those gates are large. They have degree 3. So somehow the degree 3 thing is critical somehow. If a gate has degree 3 or larger, it's large, and that seems to be really kind of capturing what we care about. So we have one gate in every path from an input to the output. We have one gate. We have one gate from the second row and one, of course, the third row. So this is going to have two large gates on any path. So this is right. So this is going to have the circuit has weft 2. I never heard this word weft before. It's supposedly related to weaving or something. So, for me it sounds like some NPR radio station somewhere, but okay. So weft in general is, just to tell you what the weft in general is of a circuit. We have a circuit C, let me just repeat it. It's the maximum number of large gates in any path from an input to the output, right? So it's the maximum number of large gates, because somehow a large gate, again, are gates that have 3 or more inputs, wires into them, okay? So dominating set as a circuit of weft 2, so it's going to belong to W2. Okay, so and the intuition here is going to be that independent set is equivalent to click, it's a very difficult problem, right? So click, it's essentially equivalent, or you know what, let me speak about the independent set. Independent set, we believe it's very difficult as far as FPT, right, to explain. We know that we believe that it doesn't have an FPT algorithm, and this problem is going to belong to W1, right? I'm going to define W1 formally shortly, right? Dominating set, we just argue, is in W2, right? Circuits that have at most 2 large gates on any path, right? And the intuition is that we can now define this class, right? So formally, WT is going to be circuits with weft circuits of weft T, right? Again, very important, and the book does not emphasize, but it is important, constant depth, right? So WT is all the circuits that have, any inputs, they have constant depth, and they have weft T, right? On any path, there are at most T large gates, right? So this is WT, and the important thing is the belief is that WT is strictly contained in WT plus 1. And the belief is that, as you climb this hierarchy, the problems become harder and harder as far as, FPT complexity. So that's why we have all this, this is why we have this definition. Okay. Okay, so what we have seen so far is 2 things, right? So I'm going to use the numbering of the book just to be consistent. Proposition 1317. Independent set. Now, we saw the dominating set is in W2. And it's not hard to see that also set cover and heating set are in W2 because it's essentially the same problem. Well, heating set and set cover are the same problem up to essentially replacing the interpretation of sets and elements. So they're really the same problem. As for dominating set, just look on the circuit for dominating set and observe that, the same circuit can be essentially used for set cover, right? Because we're going to have the element in the input, and again, for every set we're going to have an OR gate, which says you have to select an element for every set, and then we take the end of all those gates. So all those problems belong to W2, right? And maybe so this is not too surprising, right? So far so good, because this is easy to see. But maybe the more surprising result is that this is you know, that there are hard problems in this hierarchy, right? So in particular, I'm not going to show the theorem. So probably it requires quite a bit of work, but it's quite surprising. Is W1 complete? Okay. So what do I mean by that? I mean that given any problem in W1, there is a fixed parameter, there is a polynomial fixed parameter reduction, right? We're not doing regular polynomial reduction, we're doing this fixed parameter reductions. There is a fixed parameter reduction into independent set, right? So independent set capture this class, and it's very surprising, right? Because it essentially says that doesn't matter how you organize your circuit, what its constant depth is, as long as you have only one heavy gate on every path, your problem is equivalent to independent set, or if you want, it's equivalent to this very specific circuit that solves independent set. So it's a somewhat surprising result. In fact, we are kind of going to get a hint why it's true later on when we'll speak about polynomial reductions, not Turing machines. Okay, so so how do we continue from here? Okay, so let's go back to satisfiability and trisat, right? Satisfiability, the classical satisfiability is quite general, right? It allows you any circuit, but usually when we speak about incompleteness, we speak about trisat, right? Which is this canonical form of 3CNF, right? And this trisat is again this big AND gate, right, of all those OR gates, right? Okay, now, so the natural thing to say is, okay, what happened, so this is general, satisfiability is general circuits, but trisat is this very special form. So the natural thing is to ask how to get to higher level, right? So one option is to just say, I'm allowing you to alternate t times circuits where, it's formulas that alternate t times, okay? So you're allowed to have these t levels. Every level is either an AND and an OR, but all the levels are the same type, and you keep changing, right? And you do it for t levels, right? Okay. So this is going to be called 2 normalized, right? The regular trisat formula. Okay, so formally we're going to have this, so let's write it down. W0 is going to be W0 and gamma zeros are formulas formed by single literal. Right, so this is boring. Okay. Okay. And now And now you get the natural thing. Wt is going to be an O of gamma t minus 1 formulas, right? And gamma t is the end of arbitrary number end of arbitrary number of this is just, this is just deciding whether the odd level or the even level are end or O, right? So delta is, or in the top, or gate in the top, while gamma is the end in the top. Okay, and you're allowing to alternate. Right, and now we are going to call gamma t the set of t normalized formulas, of t normalized formulas. Okay. And of course, in all those problems, we need to have a parameter. So we're going to look on the weighted version. Weighted t normalized weighted t normalized satisfiability. Maybe I should highlight it or something. Right, so this is important. This is this problem, right? So what is this problem? Well, I give you a formula. I give you a formula which belongs to gamma t, and the question is there a satisfying assignment with exactly k1, with exactly k1s. Okay. By the way, you should notice that in this all this stuff about normalized formula, we don't speak about negations at all. And the reason is because if you think about it, you can always push the negation down to the input gate. So, so you can just assume that the inputs are either the values that we want, or the negations. There's going to be this difference between the two versions, but we shouldn't really care about it too much. Right. In particular, we're going to have this monotone version. So monotone. Okay, and in the monotone version, all the variables are positive, all input variables are positive, right? So the way to think about it, think about the three-set formula where there is no negations, right? And then you can ask, is there a satisfying assignment with k1s? Right, it's a monotone sat, it's, of course it's NP hard and so on. Okay, and there is of course also the version of anti-monotone. Where, every variable, every input variable is negated. Okay. Okay. So now we get a theorem that essentially tells us what are those WT classes, right? So this is theorem. Again, I'm not going to prove it. For every t, even, very important. So the following problems are W2 complete, WT complete. So let's see, what is the list? Okay, so weighted, T normalized, satisfiability, right? So given a circuit that is T normalized, that have those T alternating level of exchange, then, you know, but here we're allowing negation and so on, then, then, you know, then it's WT complete. The next version is monotone. Again, it's weighted monotone. T normalized, T norm. Satisfiability, right? And the next one is weighted anti-monotone. Monotone, anti-monotone, T plus 1 normalized. Okay. Okay, so and the second part of the theorem is about the odd T's, right? So again, weighted to normal, you know, for T larger than 3, then, you know, weighted T normalized satisfiability is complete for WT, and so is anti-monotone for T normalized and anti-monotone for T plus 1 normalized. By the way, I should say that I was wrong about the first part. Essentially because the first part is not anti-monotone. The first part is about monotone, right? So essentially what it says is that as far the normalized complexity changes only when you jump by 2, right? So T normalized and T plus 1 normalized, if T is even, belongs to the same class, right? So that's what this theorem states. So this is very nice, right? Because it really kind of captures, it tells us what, you know, how the complexity explodes as we go up in this hierarchy, right? We get more and more complicated formulas as far as the alternating levels, and the deeper the alternating levels are, the more complicated they are. Again, we are counting only the large gates, right? So W of T is all the gates of, you know, the at most T heavy gates on any path to the output. Okay, so a lot of interesting stuff is known. Right. Now, the important thing is that now that we have the complete problem, we can do reduction, right? So all those problems that we saw, like, you know, dominating set, dominating set, for example, right? Dominating set was in W2, right? Because we just had a formula for it, right? But the claim is that in fact it's complete, right? Why would it be complete? Well, the thing is to observe is that dominating set, the circuit was really, that was essentially what I argued about set cover. The circuit is just a monotone, right? It's a monotone W2 circuits, right? It's a monotone circuit. Monotone circuit with two gates, with two heavy gates on every part, with two large gates on any part. So as such, this implies immediately that this problem is W2 complete because of this part of the theorem, right? This theorem said that the monotone version of the problem, right? Monotone T-normalized satisfiability is W2 complete, but that's exactly what dominating the dominating set really is, right? So we can just, immediately reduce it, right? So now we are done, right? Or if you want, you can think about it as doing it for set cover and so on. So we get that dominating set cover, so this is theorem. Let me use maybe red. Theorem 1321. This theorem says that a dominating set cover and what was the last one? Heating set, of course, and heating set are W2 complete. Okay. Okay, next we want to speak about Turing machines and reductions. And the idea is that we want to capture this FPT stuff when we speak about Turing machine and the regular setting. So we're going to speak about short Turing machine acceptance. This is going to be a problem. Acceptance. Let's assume the spelling is correct. Okay, so what is going on? I'm going to give you a Turing machine, and by the way, I'm going to do everything very hand-wavy because life is too short. So I'm going to give you a Turing machine. It's going to be non-deterministic. But of course it has to have polynomial size. Okay. Now one important change we are going to make over the classical model is that here the alphabet is allowed to be large. Is allowed to be large. So what do I mean by large? The way to think about it is that I allow every character to have log n bits. right? The way to think about it is that really think about every cell of the Turing machine as really being, really being every input character as just being a word in the regular machine, right? So essentially it's a Turing machine that can handle words, right? So, so this model is a bit weird. It's very close to a RAM model, I think, but they want to think about it in this way. Okay, so I give you a Turing machine like that, and I give you a parameter k. Right? K is a parameter. And I'm going to ask, the question is there an execution that stops in k steps for the given input, right? Now we don't really need to worry about the input, because in all those things, since we're going to speak about reduction, you can think about the input as being hard coded into the machine, so that's not going to be a big deal. Okay, so so is the machine given the input, or just the input incarnate to it? Is there a way for is there an execution path so that it stops in k step? Now, to remind you, this Turing machine is non-deterministic, right? So naively, this problem can be solved in n o to the k, right? Because we start from the start states. The important thing is that because it's a non-deterministic machine and the alphabet are quite large, in fact, every node, every node in the Turing machine can go to a polynomial number of states, right? There's a total number of polynomial states, but every transition there might be polynomial number of possibilities. So you have to guess the next transition, and the next transition, and so on. So a path, there are n to the O of k path of length k. So this is the time it's going to take to solve this problem by brute force, right? So it kind of nicely captured this notion that of parameterized complexity, right? So we're going to show a reduction, from this short Turing machine acceptance, right? So this is just a Turing machine and a parameter k, right? And two independent sets. Okay. So some important things to remember, right? First, since the Turing machine is allowed to make only k steps, right? You care only about the first k inputs, right? Because you can read only the first k cells of the input. Right? And so you can think about that all our argument is going to be restricted to the first k cells of the machine, right? Okay. So that's one important thing. And now the question, of course, is how do we do the reduction from independent sets? The Turing machine, how do we encode it as a graph with independent sets? So the first idea is that we're essentially going to repeat the same Cook theorem idea, right? We're going to take this tape, and we really need to, what do we need to remember? We need to remember the tape during the execution, right? We need to remember the tape. And, during the execution, we need to remember the current active cell, where the the Turing machine head is, right? There is the location, there is the control state, right? And there is the time, what time we are in, right? So I'm going to build a graph with all possible, with all such possible triples, okay? Now, all the nodes that are in the same time, I'm going to build a click on them, so you can be only in one of those states, right? So that's one important thing, right? So in every point in time, you're going to be able to pick only one independent set, one vertex to the independent set. Now, the thing to remember is that we need, for this point in time, right, we need to also remember the value of this cell, right? So a vertex is going to be the time, the current time, the location, let's call it L, location, the content of the cell, and control state. Right? So each one of those parameters has a polynomial number of options, so this is going to be, and I create a graph with this, so this is a polynomial sized graph, right? Okay, so this is good. And of course I can also just, so I start from that. Okay, and now what are we going to do, right? So think about two slices of this graph, right? We have all the states, all those nodes for time t and all the nodes for time t plus 1. Okay, and we're going to connect two nodes by an edge if it's impossible to transition from this state to this state, right? And it might be impossible to transition, because, for example, by the way, in the state, I might not want to remember only the character. I might want to remember also the value of the adjacent node, this one and this one, right? So you remember the value of the tape on both sides. It doesn't really matter. In fact, I think you have to do those three states. Anyway, so between time t and t plus 1, you connect two states by an edge if you cannot transition from this state to this state, right? This means this is not valid, right? This can be invalid, for example, the most natural thing why two such states will not be valid is because the head is far, the location of the head is too far from the right location, right? To remind you, the location should be at most, one apart, because the Turing machine moves only by one location at a time, right? So you add in those edges, that all the invalid transition. If there is a valid transition, right, this is node and this node, let's assume that you can move from U to V. If there is a valid transition, you have to verify that, so the location is either the same or to the right or the left. You have to verify that the value written on the tape are consistent. This is why I wanted to have this, those padded values. Okay, so one has to be more careful than I'm describing. I'm kind of being I'm hand waving because the proof itself, as is usual with such proof, is very tedious. So let me try to be a little bit less hand wavy. So here's what's going to be, right? We have this tape of k states at time I, right? And we have those k cells. Right, of the input. For every one of those k cells, we have the value written in there. Right, so this is going to be, it's going to be ij, so k we don't need here. So we have the location I, we have the time j, and we have the value, this is j, and we have the character, sigma written in it, right? And then you can, for example, think about, as they do in some of those reductions for NP completeness, that we have a bit 0, 1. 0 says whether the head is in this location or not. And, we can also have the control mechanism state, right? We have something really long like that, right? You know, and if it's 0, then this would be null, right? And special state saying it's not relevant. Okay, now the important thing is that why are we want, so we're going to build graph with these nodes. The idea is that we're going to build this graph. It's going to be polynomially large with all those vertices. And now what we're going to do, we're going to connect any two vertices which are inconsistent as far as what's written in them, right? So, you know, for example, all the states for which there is 1, right, are going to be in a click because the head can be only in one location, right? And similarly, you know, at location j, at time I, all the cells that have the same character are going to be in a click, right? Because you can choose only one value at time k, right? So what the effect is that we have to select of this graph is that in this graph we can select only k independent vertices. Those k independent vertices correspond to the value of the tape at this time. Those k, for every cell, we're going to have one independent vertex that encode its value, right? So we're going to have these k layers of this graph, right? Every layer is going to be k, you could choose the most k independent vertices that correspond to the state of the graph. And then between those two states, you're going to put edges between two vertices if they are not consistent. So for example, you know, two cells which do not have the, you know, look on the same cell at time I, the next time, they cannot spontaneously change their value, right? If they change their value, this is not valid, right? They can change the value only if the control mechanism is there and the transition is valid. So we're going to have an edge between, you know, every position and every position in previous time that the value is different, right? And similarly, you have to encode the transition, right? You're allowed to a position with a transition only if it comes from a valid transition, right? So any invalid transition you connect by an edge and so on, right? So, you know, the details are tedious and not very enjoyable. They're in the book, but I don't think they're very useful. You know, the important thing to remember is that we're going to have a graph of k layers. Every layer we're going to choose k values that encode the tape at time k. And as such, we're going to have an independent set of size k squared in this graph, if and only if there is an accepting path of length k in the graph, right? And you know, we need to force two things, right? We need to force the start state, and we need to force the end state, right? But those two things are easy, right? Because you just put them into your independent set. You know, you build the whole graph, and then you put those states into the independent set, and you remove all the vertices that are in conflict. And now you ask for the independent set of the certain size for the residual graph. Okay, so that's it, right? So this, and you go to the reduction. You know, the important thing is that the graph size is going to be polynomial. It's not going to explode by power of k. It's going to be n to the constant. So this is all polynomial time. The reduction is polynomial time, and as such, you know, deciding if the resulting graph there is independent of size k squared is going to be equivalent to deciding if this machine can halt in k steps, which concludes this proof. Okay, and let's see if I want to tell you anything else today. Okay, so I think I skipped one thing that I did want to show you. I don't know how I successfully did this. Okay, so the final thing I wanted to say for today's lecture is that the observation that this short Turing machine acceptance, we reduced it to independent set of size k, right? If this, so this is Turing machine and k, and we showed that this reduces to instead of independent set of size k squared. Is there in the generated instance independent of size k squared. But independent set is of course W1. Independent set is W1 complete. So that shows that short Turing machine acceptance is in W1. Great news. And in fact, it's not hard to show that there is a reduction in the other direction. There is a fixed parameter reduction from independent sets with parameter k to a short Turing machine acceptance. We will see reduction like that in the next lecture, which means that we get the following result, theorem, short Turing machine acceptance is W1 complete. So, you know, it belongs to the first, the bottom of the hierarchy, which is somewhat surprising. Okay, that's it for today's lecture.